You can start, sir.
Okay. Hello, this is Gulab Dewangan. So I'm going to talk on active galactic nuclei. So I have two lectures today and tomorrow. So we will go through the basics of active galactic nuclei and a little bit on the current status of understanding of the central engines in active galactic nuclei. So here I list the reference books. So the first one, then Introduction to Active Galactic Nuclei by Bradley M. Peterson, is a very introductory book. And if you are just beginning to in this area, then I would recommend to go through this book. The other books are slightly more advanced. The book by Walker Beckman covers more on central engine and an excellent book for Asian physics. The third book, The Physics and Evolution of Active Galactic Nuclei by Guy Natcher, is an extensive overview of active galactic nuclei, not only the accretion disk hot corona, but as well as the optical narrow line region, broad line region, and connection to galaxies. Everything is covered in this book. And if you are really interested in learning high energy astrophysics, which covers lots of topics, particularly different kinds of compact objects, white dwarfs, neutron star, black holes, as well as active galactic nuclei, you can refer this book. Okay, so let's begin. So the first question is, what are active galactic nuclei? So the name suggests, of course, these are nuclei of galaxies. And how do we identify these active galactic nuclei? So let's imagine we are taking a photograph of a galaxy, take a very short exposure. And if there is an active galaxy, then what you see in the short exposure is a star-like object, a point-like object in the photograph. Okay. While in the normal galaxy, you may not see, because the exposure is very short, you may not see anything. Okay. And if the galaxy is bright, then you start seeing diffuse emission. So you keep on increasing the exposure time. Then in case of active galaxy, this point-like source will become brighter and brighter. And in normal galaxy, you will start seeing diffuse emission. And at some point of time, you keep on increasing the exposure time, you will see the diffuse emission from host galaxy, even in case of active galaxy. And you will see, of course, the galaxy in case of normal galaxies without an active nucleus. So what I want to say, if you observe a bright nucleus in galaxies at the center, if the centers of galaxies contains a very bright nucleus which may overshine the entire galaxy, we call this particular galaxy host an active galactic nucleus. And such objects, such galaxies, we call active galaxies. Okay, so they are identified by the presence of a very bright star-like nucleus, and the light from this nucleus itself can overshine the entire galaxy. So this is how we find observations. Of course, there are different techniques at other wavelength also, but this is how you easily identify active galaxies. There are other signatures of the activity at the centers of galaxies. For example, here this is an optical image of another AGN. So first of all, you see here very bright nucleus, and it is in addition a jet-like structure is you are seeing it originating from that nucleus. So this jet-like structure is also a sure signature of the presence of active galactic nucleus. Okay, so any object is called an active galactic nucleus if the activity at the center is in substantial, so in some characteristic way which can be determined observationally. For example, in this case, jets from nuclei, and we had seen earlier very bright point-like nucleus. Then we will see some of this agent will have broad emission lines in the optical or UV spectrum. So these are the signatures of active galactic nuclei, and there are many more which we will see again. Okay. Here is another example. Sometimes the centers of an active galaxy may have obscuring material such as dust and cold gas. Okay, in such case, because the light cannot easily pass through the dust and thick material, you will not see a very bright nucleus at the center. But if you look at the same galaxy and take high resolution images in the X-ray band, because X-rays can penetrate this material, then again you will see a very bright star-like or nucleus at the center of a galaxy. And this is again a sure short signature of an active galactic nuclei. So an X-ray point-like source at the center of galaxy is another characteristic of active galactic nuclei. So there are a number of different types of active galaxies. So the main ones I have listed here. One main class of AGNs are called Seaford galaxies. They are discovered by Carl Seaford long time back. And these Seaford type AGNs are hosted in spiral galaxies. And the luminosity or the radiation output from the active nucleus, that is from the center region only, is comparable to the luminosity of the entire galaxy, which consists of about 10 to the power 11 stars or so. So just one nucleus emits as much as energy is the entire or all the stars in that galaxy. So the AGNs are that much powerful in Seaford galaxies. The other classes are radio galaxies. The radio galaxies emit a strong radio emission. That is why they are called radio galaxies, and they have jets and lobes. We will see some of these structures, but the radio power is high in radio galaxies. Then we have quasars. Both this can be radio quiet as well as radio loud. They are often hosted in giant elliptical galaxies, where the luminosity of the nucleus itself can be about 100 times the luminosity of the entire galaxy. So the quasars are the most powerful active galactic nuclei, and as you see here, they are much more powerful compared to the AGNs in Seaford galaxies and radio galaxies. How do we identify Seaford galaxies? So Seaford galaxies are generally identified from their optical spectrum. And when you look at the optical spectrum, you will see the spectrum like this, which is shown in this figure. First of all, you will see a very strong continuum emission in the spectrum. The spectrum, when we say, it is essentially the flux as a function of wavelength, frequency, or energy. And very strong continuum means there are lots of photons in the continuum where there are no lines. In addition to that, you see very broad emission lines like this. This broad emission lines is due to the H alpha line. Then there are H beta line here at 4861 angstrom. Similarly, other lines H gamma, H delta, etc. And at shorter wavelength, you will also see carbon 4, limon alpha, magnesium 2, etc. So if you look at carefully, the all permitted lines are broad, and the width of these lines is measured in terms of the full width at half maximum of this line profile, and the full width at half maximum of these broad lines can be of the order of 5,000 kilometers per second, and it can range from few thousand kilometers per second to 10,000 kilometers per second. What it means is that the material which is giving rise to this broad emission lines actually moves with this 5,000 to 10,000 kilometers per second speeds. Okay, and in addition to this broad emission lines, so there are this narrow emission lines. For example, here you see very close to this broad H beta line, the oxygen 3 line at 5,007 angstrom as well as 4959 angstrom. These lines are much narrower, and you see the width of these lines is about 500 kilometers per second, which is about 10 times smaller compared to the widths of these broad emission lines. Okay, so these Seaford galaxies show two sets of emission lines, the broad emission lines and the narrow emission lines. And the lower panel is essentially expanded view of the spectrum, and here I wanted to show that below about 4,000 angstrom there is a excess emission compared to the continuum in other parts. This is called small blue bump, and this is due to a number of transitions in the iron 2 element, so-called the iron 2 complex, as well as due to the Balmer continuum emission. That means the electrons in the continuum combining are making downward transition at n equal to 2 level, that the emission they give rise to this emission which falls in this big blue bump region. This is a small blue bump region. There is a big blue bump as well, which we will come to know later. So these are the characteristic spectrum of Seyfert galaxies. Radio galaxies, let me briefly say how the radio emission was discovered and how the radio galaxies were identified. So the radio emission was discovered from our galaxy by Jansky in 1933. And this emission has a power-like spectrum, and it also has high degree of polarization, and these characteristics are essentially ensure that the radio emission is due to the synchrotron process. That means high energy electrons moving in magnetic fields, and they give rise to this radio emission. And once these radio emissions are observed, because the synchrotron radiation is produced by high energy particles, so and moving in magnetic fields, so the role of this energy particle and cosmic magnetic fields were realized very quickly, and that's how birth the modern high energy astrophysics began. Okay, and once this radio emission was discovered, then people did survey the sky for radio sources, and these radio surveys revealed large population of galactic and extragalactic radio sources. Some of these radio sources, newly discovered radio sources, were identified with Cassiopeia A. This is supernova remnant. The supernova remnants are also strong sources of radio emission. Some others were identified with galaxies. For example, one of the radio source, Cygnus A, was identified with a galaxy at a redshift of 0.057. And this is a radio image of Cygnus A, and you see here there are this radio emission is you see a very compact center here, which coincides with the optical center of the galaxy Cygnus A, and then a narrow jets emanating from the center and connect to these large structures called so-called lobes. And at the edge of the lobes, there are something called very bright compact regions called hot spots. So in both sides. So this is a typical structure of radio emission from radio galaxies. They are much more powerful. Radio emission from these radio galaxies is much more powerful. For example, the radio emission from Cygnus A is about million times more powerful than the radio emission from our own galaxy, Milky Way. Okay, so radio galaxies are associated with bright radio sources. They are very much powerful radio emitters than our own galaxy. Typical radio power of at 1.4 gigahertz, less than about 10 to the power 23, is very common in normal galaxies, normal spiral galaxies, and this is due to the synchrotron emission in the supernova remnants. The powerful radio galaxies have radio power at 1.4 gigahertz more than 10 to the power 25 watt per hertz. That means they are more powerful by 100 times or so compared to normal galaxies like our own. Okay, and there are weak radio galaxies with the power between these two limits. And what people found that the most powerful radio sources are associated with optical star-like objects, and therefore they are called quasi-stellar radio sources and are quasars. And this is one example of the radio source, the 3C273. This is the third Cambridge catalog, 273rd source in the third Cambridge catalog. And when people identified the radio source and with the optical source, and here is the optical. So you see, this is just like a star, and you see some of there are other objects which are really stars. So this object, this radio source, this optical source identified with the radio emission, strong radio emission, also looked like a star. And of course, there is some structure here, but people didn't bother too much in the beginning, but they just saw a star-like object. And when they took the optical spectrum of this star-like object, what they found? They actually found the emission lines due to S beta, S delta, S alpha, etc. But they found the emission lines, but they were not able to identify. And to identify lines, these emission lines, what you do, you compare with the spectrum and the lab and look at the locations of the line. They could not identify these lines in the spectrum of this radio source. But careful comparison showed that they can actually match if the lines are red shifted. That means shifted at a longer wavelength. And then they can clearly identify, okay, this object has S beta, S gamma, S delta, and other lines as well. So this way they could determine the redshift of 3C273, and it turned out to be 0.158. And at that point of time, this was large redshift. Of course, we today know redshift of 6 and even higher. So what is the importance of the significance of this such a high redshift is even 0.158. So once you have the wavelength shift, that from that you calculate the redshift. And once you have the redshift, then you can estimate the distance using this formula D S0D is equal to CZ of essentially Hubble's expansion. So then distance of this object turns out to be 470 megaparsec. Okay, and that's a huge distance. 1 parsec is 3.26 light year. Okay, so you are talking about a billion light, more than a billion light year. So the light from this object takes more than billion years to reach to us, and that's a huge distance. And if you are observing an object from such a huge distance, that must be, this object must be intrinsically powerful. And you can find that actually, given the distance, you can find out what is given the distance and the observed magnitude. If you are aware of basic astronomy, then you understand the magnitudes, etc. But these are measure of the light output. Then you calculate something called absolute magnitude, which is minus 2.5.3. And even if you do not know this magnitude system, but when you compare this magnitude for other galaxies, then you will see the importance of this. So let's see, how does it compare with the normal galaxies? How does this magnitude compare with the magnitudes of the normal galaxy? So what is the absolute magnitude of Milky Way? Milky Way's absolute magnitude is minus 20.5, and then you can compare using this relation, and m is equal to minus 2.5 log of this luminosity and constant. You can write down this equation for Milky Way as well as for 3C273, and then you can find out that the luminosity of this quasar 3C273 is nearly 100 times brighter than the normal galaxies. So this that star-like object is 100 times more powerful than the entire Milky Way, and that means it is emitting huge amount of power. So let's go through the characteristics. Some of the observational characteristics of these agents I have already pointed out, but let's go through a little more detail. As I mentioned, they are the nuclei of galaxies, and these nuclei are unresolved. Therefore, their sizes are much smaller than 1 parsec, or about a light year or so. So this bright point-like nucleus, whose flux can often exceed the flux from the rest of the galaxy. Here you see this nucleus is very bright compared to anywhere in the galaxy. These are other examples from ground-based telescopes. So in all of these are Seyfert type agent, and you see very bright nucleus in all of these objects. These are some other images taken with the Hubble Space Telescope, and again you see very bright nucleus, but you also see some kind of a disturbed morphology in these objects, which may be indicating the fueling of these agents. As I mentioned, they are point-like objects in the optical ultraviolet as well as in X-rays. But if you look at in their radio, you have already seen the radio image of Cygnus A. They have huge lobes. There can be jets. So in radio, they are not point-like objects. They have peculiar structures, and some of the examples of the structures are shown in this image 3C315. You see the nucleus and the structures, and symmetrically in both sides of this nucleus there are the various different kind of radio morphology. So what are the other characteristics? They have a very large luminosity. The luminosity from AGNs can range from 10 to the power 42 to 10 to the power 48 ergs per second. And if you compare this luminosity range with the luminosity of our sun, which is 2 into 10 to the power 33 ergs per second, that means these objects have luminosity something like 10 to the power 9 times, 10 to the power 15 times the luminosity of sun. Okay, they are so much powerful compared to our sun. And if you compare the luminosity of these AGNs with the luminosity of our galaxy, like our own, our galaxy has about 10 to the power 11 stars, and if you assume sun-like luminosity, then our galaxy has roughly about 10 to the power 44 ergs per second. And that means if you compare this with the luminosity range of AGNs, then the AGN power output ranges from about 1/100th of the luminosity of a normal galaxy like our own to about 10,000 times the luminosity of a typical galaxy. So this is the range of luminosity, about 1/100th to 10,000 times the luminosity of a typical galaxy. And there are, when you try to measure the luminosity, there are of course some complicating factors. For example, in some objects, there may be a central dust layer passing through the nucleus. So in this case, the luminosity may be underestimated. Then in some other cases, there are relativistic beaming. If in such cases, you may be overestimating the actual luminosity. And if you look at the spectral energy distribution of these AGNs, they are very different compared to the spectral energy distribution of normal galaxies. So in this figure, in the right hand side, you see the spectral energy distribution of normal galaxies, which is confined in a small range of frequencies, about 10 to the power 13 to about 10 to the power 15 hertz or so. So why is this so? Because normal galaxies, as you know, they contain stars, and different kinds of stars, of course, from cool stars to hot stars. And the temperature of these stars can range from few thousand Kelvin to about maybe 20, 30,000 or 40,000 Kelvin. And the stars are emitting like black bodies. So this spectral energy distribution, or the spectrum of normal galaxies, is nothing but the sum of black body emission from stars, and the temperature of these stars ranges from about few thousands to tens of thousands. So therefore, their emission is confined from, let's say, from near infrared to ultraviolet or so. While in the case of AGNs and the solid data points are essentially the flux measured, or the spectrum measured from a C41 galaxy called NGC 3783. And here you see that unlike in normal galaxies, which have lower and lower power output when you go to higher frequencies, or even at lower frequencies in the below infrared region, they have much stronger emission. In fact, their emission rises in the ultraviolet, and it can go the strong sources in the X-ray and sometimes in the gamma ray also. And in the infrared side also it rises, but then depending on whether it is a radio loud AGN or radio quiet AGN, there's the radio power. They are radio emitters, but sometimes radio emission can be higher, sometimes it can be lower, depending on radio loudness parameter. Okay, so this is the difference between the spectral energy distribution of normal galaxies and active galaxies. This is another example of the spectral energy distribution of a particular type of agent called blazars, where we think they have jets, strong jets, which is pointing towards us. And due to the relativistic beaming, their emission is much more stronger. So again, you see the spectrum spawns from radio, optical, ultraviolet, extreme ultraviolet, soft X-ray, hard X-ray, and even very high energy gamma rays. So that is the kind of spectrum from these objects you see. They essentially emit over the entire electromagnetic wave band from radio to gamma rays. Okay, so this then the agents also have very strong emission lines. For example, you see here, you have already seen the spectrum of Seyfert galaxies, but here I show the spectrum, optical spectrum of different types of agents and compare with the spectrum of normal galaxies. If you see the normal spectrum of normal galaxies, first of all, you see this noisy kind of spectrum, and this is because the continuum is not strong. Apart from that, you see absorption lines. These are essentially due to the stars. Compare this to the spectrum of Seyfert galaxies. So here you see very strong continuum, and as I had mentioned, the broad emission lines as well as narrow emission lines. And when you see these two sets of emission lines, both broad and narrow, such a Seyfert galaxies are called type 1 Seyfert galaxies. On the other hand, if you only see these narrow emission lines and this continuum, then they are called type 2 Seyfert galaxies. Then we have broadline radio galaxies. That means that they are radio galaxies, but they also have broad emission lines in this case, like the Seyfert ones, but they are radio loud. So they are called broadline radio galaxies. There are also these narrow line radio galaxies where you see the narrow emission lines. You do not see the broad emission lines, but they are radio loud. They are powerful radio emitters. So they are called narrow line radio galaxies. Then there are some agents like the one I showed earlier. So the so-called BL lake type agents. Some again they are very powerful objects, and they have very strong continuum, but no emission, no emission absorption line. Only sometimes you see very weak absorption, but these spectrum are almost featureless. In such cases, the emission from the jet is dominating completely any other components. That's why you see the jet emission, which is devoid of this emission and absorption lines. Here is the mean spectrum of quasars. So radio loud as well as radio quiet quasars. So you see this strong continuum which rises in the blue side, and of course there are these broad emission lines as well as these narrow emission lines. There are other types of agents. They are not very powerful, but they have the emission lines like the Seyfert 1 galaxies, Seyfert 1 or Seyfert 2 galaxies, and continuum is not very strong, but because of this emission lines, etc., they are classified as LINS, low ionization nuclear emission line region galaxies. They are low luminosity agents. So the quasars are the most luminous agents. Then Seyfert galaxies are the other slightly less powerful agents, and the LINS are the least powerful agents. These are the different types of optical spectra of active galactic nuclei. And these agents also have strong X-ray and gamma ray emission. I have already shown that. Then the agents show strong variability at almost all wavelengths from time scales varying from a few minutes to days. And here are some of the examples of this time variability of some of these agents. For example, you see in the top left panel here, the X-ray intensity is plotted as a function of time. And this X-ray intensity is varying very wildly, sometimes by a factor of more than 100 here. So this is some agents show this kind of a strong, rapid, and large amplitude variability. Okay. You see in the here in the right panel, top right panel, there is a light curve of this emission line. So these are the extent of the flux of this emission lines: carbon 4, lime alpha, magnesium 2, again plotted as a function of time. You saw the lines, the emission lines are also varying in their intensity as a function of time. And here you see the optical ultraviolet continuum emission. The continuum emission is 1350 angstrom, 1840 angstrom, and 2670 angstrom. The continuum is also highly variable, like the, in fact, more strongly variable compared to the line emission. Not only in the X-ray and optical UV bands, so these agents can be very variable in the radio in the emission also. For example, this is the time series are the light curve of radio intensity at 38 centimeter wavelength. So you see the radio emission is also very strongly variable. So what we see, the agents are variable at various wavelengths. Of course, not a single agent may not be variable at all wavelengths. But for example, the radio loud agents or the blazars will be variable in the radio, while radio galaxies and Seyfert galaxies, they do, though they emit some amount of radio emission, may not be variable that at that high. But there are agents which show extreme variability in different bands. Okay, so there are about 10 to 15% of agents that are emit strongly in the radio emission, and I have already shown this picture, a radio picture of Cygnus A, and here you see this core. The size of this core is about a milli-arcsecond, and this coincides with this optical center of the galaxy. Then from this core or the nucleus, there are jet-like structure which are emanating and connecting to this so-called this radio lobes, and at the edge there are these hot spots. And the typical sizes of these jets can be from parsecs to kiloparsec scale, and the lobes can be at about 100 kiloparsecs. Sometimes the sizes of this, the distance between these two lobes, two opposite lobes, can reach up to megaparsec or so for the giant radio galaxies. So these are the typical structures of these radio galaxies. If you look at this radio galaxies carefully, then one can identify three different distinct emission regions in radio galaxies. First, of course, we have seen this diffuse lobes on kiloparsec to megaparsec scale. Then narrow jets, which actually arise from the nucleus and connect to hotspots. And the compact sources which coinciding with the optical nuclei. And when people monitor this compact nuclei in some of the radio galaxies, what they found that the structure is changing with time. For example, here is the radio observation of this quasar 3C273 at 2.8 centimeter, and this you see this structure. This is the nucleus and some other structure, some kind of a blob getting ejected from this one. And you see in 1977, you see that separation between these two. In 1978, this the blob has moved a little further. In November 78, this blob has moved even further. Another the blob is getting ejected, and similarly, and so on. So that this blob seems to be moving away from this galaxy, and with this kind of observation, people can estimate at what speed this blob is actually moving, because the separation they can find out from here. So what they find out, very surprisingly, that in this galaxy 3C273, this source component, this blob, is moving with at a speed of apparent speed of 8 times the speed of light. So at Z equal to 0.158, the hotspot in the radio jet moved 25 light years in 3-year period. So how is it possible? Is it violating the special relativity? Not really. So here is such a motion, apparent motion with speed more than the speed of light is called the superluminal motion, and one can easily understand the superluminal motion here. For example, let's say there is this quasar, this nucleus of this active galactic nucleus here, And let's say at time t equal to 0, there is a blob ejected from this quasar, and this information reaches, because this object is located at a distance d, capital D. So therefore, this information that a blob has been ejected reaches to the observer at a distance d after t is equal to d by c. So this is the distance divided by the speed of light. Okay, so now let's say after time t1, this blob is moving. This blob moves moves a distance v times t1, where v is the speed. So this blob is moving with the speed v. So therefore, in time t1, it has moved a distance v t1. Okay, and this information reaches to the observer at time t2. This time t2 will be this time t1, which this blob has taken to move from after getting ejected, a distance vt1, and then this the time it requires to reach to the observer, and that time is of course this d by d minus this distance d, and because the blob has already moved a projected distance of vt1 cos theta, this distance, so you will have to subtract, because that much distance has been traveled by the blob, and divide by c, of course. So you can, and the projected separation is vt1 sine theta, and you can calculate how, at what speed this this is actually moving. The projected distance is getting enlarged. So the transfer speed of this component you can calculate. So this will be vt1 sine theta divided by the time difference t2 when we observe the blob at the projected distance vt1 sine theta, minus the d by c when this blob actually was ejected. So you can rearrange these things. What you will get, that the projected speed is v sine theta divided by 1 minus v cos theta by c. So v by c, of course, you can write beta. So you can maximize this v projected speed, and when cos theta is equal to v by c, and you could substitute here. So therefore, the projected speed you can find this gamma Lorentz factor times the speed v, because the Lorentz factor can be large, more than 1, of course. So the apparent motion with this speed v greater than c, this speed v, projected speed v greater than c, can be observed very easily without violating the theory of special relativity. This is due to the very high speed at which this blob is moving, and it is moving very close to the line of sight. Because of this two facts, it gives an apparent motion which is more than the speed of light. Otherwise, it does not violate this special relativity. Okay, so these are the observational characteristics. Just to summarize, they have very large AGNs have very large luminosity of the order of 10 to the power 9 to 10 to the power 14 times the luminosity of our sun. The entire luminosity is coming from a very compact region, with the size of which is much smaller than about 1 parsec. Their emission, they emit broadband continuum emission from radio, quite AGNs of definitely from IR, infrared to X-rays, and sometimes in gamma rays. And if you look at the luminosity per decade in frequency, it's roughly constant. Okay, the radio loud agents also emit very strong radio emission, and the blazars also emit very strong gamma rays, low energy gamma rays, as well as very high energy gamma rays. These AGNs, most AGNs show very strong emission lines in the optical and ultraviolet. AGNs are strong emitters of X-rays, and some are very bright in gamma rays as well. Many types of most AGNs show strong variability over the entire electromagnetic wave band, and the time scale of variability can range from a few minutes to days and months. Some at about 10-15% of AGNs are radio loud, so they show strong jets and lobes in their radio structure. So these are the basic characteristics of AGNs. Let's now look at how such a high luminosity is generated in AGNs. What is the power source? So let's look into the AGN energetics. So we need to find the total energy output. So total energy output. So the total energy output, we know the luminosity, and if you know the lifetime we can roughly calculate the total energy output. And luminosity is about, let's say, 10 to the power 45 ergs per second or so, typically, for the variety region. Lifetime, we are not sure about the lifetime, but we know that roughly one galaxy out of 100 galaxy actually hosts an AGN. And given the age of the universe, we can say that the lifetime of these AGNs is about 10 to the power 8 years. So you multiply 10 to the power 8 years, and the luminosity, you will get the total power, the total energy output is about 10 to the power 61 ergs in these agents. The same number you can also reach by considering the radio loud agents, because in the radio loud agent, the radio emission is from is due to synchrotron process, where high energy electrons are moving in a magnetic field. So you can, given the radio spectrum, you can estimate the total energy in the particles as well as in the magnetic fields. And then you sum over the entire volume of the source, then again you will find that the total energy content in these lobes and hotspots is about, again, 10 to the power 61 ergs. So the question is, how do we produce such huge amount of energy, 10 to the power 61 ergs, in these agents? So people spend a lot of time in investigating this. So let's begin how people reach the final conclusion about the origin of this such a high luminosity. First, the time variability. This gives us the size of the emission region, because we cannot resolve the sources. So we need to therefore we need to use time variability argument to estimate the size of the emission region. So assume that the state of the emission region is changed by a physical process. So let's say you have some kind of a medium. You can assume for that matter a spherical medium. So then something happens at this, let's say at the center, and this disturbance then travels to the entire region, and that time scale. The time scale for that physical process to change in order to generate that disturbance, and how fast this disturbance travels to other regions. These two things essentially determine the variability time scale. So one is a tau process, which is the time scale for the radiation process, and the other is the delta T, which is the crossing time needed to cross the emission region. And the crossing time is much larger than the time scale for the radiation process. And if the state change spreads with speed v less than c, of course it has to v less than c, it cannot exceed the speed of light, then the size of the emitting region, you can easily calculate L size equal to v times this delta t, which is less than c times delta t, because v, the speed at which the disturbance travels, is less than the speed of light. For the observed time scale of variability, the T observed, which we observed on which the flux varies or the luminosity varies. This observed time scale T, delta T observed, is essentially combination of tau process, the time scale for the radiation process, and delta T, this crossing time. So from this we see that in any case, the size of the region must be less than or about the speed of light times the variability time scale, observed variability time scale delta T. So if we say, okay, the flux is changing by a factor of 2 in 100 minutes, then the 100 minutes into speed of light, that gives us the typical, that gives the size of this emitting region. Okay, so about the observed time scale, in the optical ultraviolet band, the observed time scale is about 1 to 10 days. So roughly in these 1 to 10 days, the optical continuum can change by a factor of 2 or so. So this 1 to 10 days translate into a size scale of 0.001 to 0.01 parsec. While in the X-ray band, if you look at the time variability, X-ray is very much faster, and the variability time scale is about an hour. Okay, in that case, the size scale is about 10 to the power minus 5 parsec, which is very compact. And if you compare this size scale with the Schwarzschild radius for different masses, so you consider million solar mass. So the Schwarzschild radius is 10 to the power minus 7 parsec. 10 to the power 8 solar mass, and 10 to the power 9 solar mass, you reach to like this X-ray variability size scale 10 to the power minus 5 parsec or so. So it already kind of suggests that the variability, unless the variability occurs in the vicinity of the supermassive black hole, we will not observe such a rapid variability in the X-ray band. So let's now look into the power source. So we know that the total energy output from a quasar is at least the energy stored in the radio halo, which is about 10 to the power 61 ergs. And using this Einstein's equation E is equal to mc square, if you want to generate 10 to the power 61 ergs, then you will need to completely burn 10 to the power 7 solar mass to generate that huge amount of energy. And of course, in any process, any mechanism, you cannot completely convert matter with 100% efficiency into energy. In fact, the nuclear burning, for example, the hydrogen burning has an efficiency of about 0.6% only. So that means in order to convert 10 to the power 7 solar mass completely to energy, you need to have at least a 10 to the power 9 solar mass at one place in that compact region. Okay, and because this rapid brightness variation, so that the size of this where this 10 to the power 9 solar mass should be kept is no bigger than a solar system. You see 10 to the power minus 5 parsec or so. Okay, and if you have such a huge mass into a compact region, then you can calculate the gravitational energy release using this formula 3 by 5 g square by r. This is the gravitational potential energy, and if you want to assemble such a configuration, then this amount of energy will be released. And if you calculate that, it is about 10 to the power 62 ergs, which is 10 times larger than the nuclear fusion energy. So the conclusion is that, which was given by this model was given by Donald Lindenbell in 1969, and is in his own in his statement says evidently, although our aim was to produce a model based on nuclear fuel, we have ended up with a model which has produced more than enough energy by gravitational contraction. The nuclear fuel has ended as an irrelevance. So what the conclusion is that the gravitational energy release as the matter accretes onto the compact object, that obviously the gravitational energy release can power these powerful active galactic nuclei. So let's go through how people estimate the masses of AGN, and so this masses, of course, there are accurate methods, more accurate techniques, but let's go through how one can easily estimate by measuring the luminosity. So because these objects are continuously emitting objects, and they are, as we saw, their masses must be high. So there is a strong gravitational force inward. So because of the huge masses involved, and as the energy is produced, these photons will strike to the material material coming closer, or material bound to with this gravitational force. So therefore, there is outward radiation pressure force. So that means in order this object survive for a long time, then there has to be some kind of balance between the inward gravitational force and outwards radiation pressure. And when you balance this, then you can find this limit called the Eddington limit, and that helps in estimating the mass of these objects. So let's see, how do we estimate the Eddington luminosity? So we have a capital object with a mass capital M, and at a distance r, there is a material which is with a small mass m, which is being accreted with an accretion rate controlled by this momentum transport from radiation to this small mass m. So there is a gravitational inward pull and outward radiation pressure force. So the gravitational force, of course, is gmm divided by r square, the separation. And the outgoing photons from the small mass m scatter off the secreting material small mass m. And if you have the luminosity L, which is the luminosity due to this accretion, then the number of photons crossing at a radius r per second per meter square, that will be given by L divided by 4 pi r square, and you divide again by the energy of the photons. So you will see these photons per meter square per second. And the scattering cross section is the Thomson scattering cross section. So the number of scattering per second will be sigma t multiplied by this quantity. Okay. So and the other thing is the momentum transferred from photons to particles. So if a photon is striking with this electron proton pair, then the momentum transferred is h nu by c. Why I'm writing here electron and proton pair? Because the Coulomb force binds these two particles. Okay, so the momentum gained by particle per second is essentially force exerted by photons on particles. So therefore, one can write down the radiation pressure force. Somehow, this formula is not coming up, but you multiply this quantity with the number of scattering we found here. So that gives us the radiation pressure force. Unfortunately, some of these formulas are not coming up. Okay, so the thing is that when you equate the radiation pressure force and the gravitational force, then what you get is this equation, which we call this Eddington luminosity. So the Eddington luminosity comes from by balancing this gravitational inward pull and outward radiation pressure force. So here 4 pi c is the speed of light, g is the gravitational constant, capital M is the mass, and mp is the mass of that matter which is being accreted. In each, actually the photons, the scattering occurs on electrons, but the electrons and protons are bound to make a pair due to the Coulomb interaction. So therefore, when we use the mass, we need to use the mass of the proton divided by the Thomson scattering cross section. You can put the values of these things and put the mass, capital mass, in units of solar mass, 2 into 10 to the power 33 grams per second. Then you can find the Eddington luminosity. Since the observed luminosity should be smaller or less than about L, the Eddington luminosity, otherwise the radiation pressure force will push everything, and the object will not be a stable object. So that means the mass must be more than about L, the luminosity, divided by 1.3 10 to the power 38 solar mass. So for a luminosity of 10 to the power 46 ergs per second, the mass must be greater than 10 to the power 6, 1 million solar mass. So if the object is emitting 10 to the power 6, 10 to the power 46 ergs per second of luminosity, the mass definitely must be more than a million solar mass. So you see, large luminosity implies to huge masses. So here is a kind of a physical picture based on our arguments. So high luminosity, as we just saw, if objects we can measure the luminosity that are high, and if you apply the Eddington limit argument, that leads to large mass. As we saw, 10 to the power 46 ergs per second results in the mass more than million solar mass. And these objects are highly variable. They are very, very small size. So the huge mass, more than about million solar mass, is confined into a very small size, less than the size of the solar system. In physics, we do not know anything other than the black holes having such properties, huge mass confined to in a small region. That is why we call these objects host black holes, supermassive black holes, because their mass is very high. And the accretion of material onto the supermassive black hole essentially generates this huge radiative power which we are observing in different bands. So the things to remember is that the active galaxies host supermassive black holes at the center. The mass of these black holes can range from 10 to the power 5 to 10 to the power 10 solar mass. They are powered by accretion. If you have an accretion rate m dot, they produce luminosity, which can be written as m dot c square multiplied by eta. Eta is the efficiency, and efficiency is about roughly about 10%, 10 to 20% or so. The size scale you can measure with this this fossil radius given the black hole mass of mbh. The Schwarzschild radius is 2 gm by c square. The luminosity is of the order of Eddington luminosity, which we obtain by balancing the radiation pressure force and gravitational force. And typical luminosity given the mass is this 1.3 into 10 to the power 38 when black hole mass is written in units of solar mass. So these are the things to remember when you consider AGNs. Okay, I think I will stop here. We have about 5 minutes, and I would like to hear questions from some of you. Questions, please. You can raise your hand. Okay, so Sachin.
Okay, good morning, sir. So my question is related to like when you explain that the lobes were exceeding the host galaxies, and we can like calculate the velocity of that. So my question is, do the velocity remains constant for like suppose we are calculating for the Seyfert galaxies? So do the velocities from which they are exceeding remains constant throughout, or they changes?
So you are talking the velocity we measure with the emission lines?
Yeah, sir.
Okay, so the emission, when you, this is a good question. So as I had mentioned, if you look at the emission line flux and the continuum flux, both change. So that means the emission line profile changes, and obviously the emission line intensity changes. Usually the width of the emission lines can change, but very slightly. So the speed at which they are moving around the black holes, that is why you get this velocity broadening that remains more or less constant. Sometimes what happens, because of the change in the luminosity, the line emitting region, for example, if you think of H beta line emitting region, that region may change slightly, and if that changes, then the distance between this region, the separation between this region and the supermassive black hole can change slightly, and therefore the velocity, it can change slightly but not much.
Okay, thank you, sir.
Okay, thank you. Neil, can you ask your question?
Hello, sir.
Yes.
So mine is a basic question.
Yeah.
If I have the spectra of a radio loud galaxy, and that of a Seyfert galaxy, then they look almost similar.
Yes.
In that case, how do we know whether a galaxy is a Seyfert or a radio loud?
Yeah. So in that case, you look at the radio emission and compare with the optical emission. So and there is a parameter called radio loudness parameter, which is essentially the ratio of radio emission and the optical emission. And based on that, you determine whether this object with emission lines is radio loud or radio quiet. If it is radio quiet, then you say it is a Seyfert galaxy, and if it is radio loud, you say it is a radio loud galaxy, and it could be one of the broadline radio galaxy or narrow line radio galaxy. Okay.
Yes, sir. Thank
you. Yeah. Any other question?
Hi, Gulab. Gulab, this is Saikya here.
Yes, Professor Saikya. Yes.
No, before you actually sign off, I will just take a gallery picture of the participants, So once the questions are over.
Yeah, sure. I don't see other questions. So I don't know if there is other board where the participants can ask questions, Slack or something. They can.
In the chat, there is a question by Rabiul Islam on what are hotspots.
Okay. So hotspots we observe in radio galaxies, as you saw the picture of Cygnus A, where at the center we have the core from where this the jets are emanating, and they are connecting to these lobes. and essentially the jet is moving in the intergalactic medium, and depending on the material in the medium, there is a interaction or generation of shocks, etc. And this place where this jet interacts with the medium, and the particles get accelerated there, and that's the region where this hotspots forms. Okay. Are there any other questions?
Khushbu asks, what are the cause of flares?
The cause of flares. Okay, so the variability, I think this question is related to the variability where we saw the light curves and the flux. For example, the X-ray flux can rise by several factors, sometimes factors of 100 in several days, and we normally we see very often a factor of 2 variability in the X-ray intensity in on scales of hours or so. So the question, what is the origin of such variability? So that's a very good question, and it is not clearly known, but generally what happens, the objects are powered by accretion of material, and in some way, if you can change the accretion rate in short time scale, of course, then you can generate more luminosity, and the inner regions of the accretion disk can have a certain kind of instability where it can drive change in the accretion rate. And if it is happening very close to the black hole where the X-ray emission arises, you can generate these flares. And small scale flares in X-rays can also be generated with so-called magnetic reconnection, because this accretion disk and the inner plasma is supposed to have magnetic field where the field is frozen into plasma. And if such plasma with different polarity, magnetic field polarity, come into contact, then they can combine and they can produce huge amount of energy, which may be powering some of these flares. Okay.
Okay. So Gulab, if you stop sharing, I'll just put the gallery.
Yes.
Sort
of. Okay.
So could I request you all to put on your videos just for a gallery shot, very brief one? Yeah. So Deepa, Shruti, Sabita, Prem Prakash, Achyut Kaushik, Ayush Garg, Jyotirmay. So could I request you all to put your videos on? Pallavi Day, Kaushik Banja, Haribala Krishna, Samik Datta, Achyut Kaushik. We're still missing some who are not putting their videos on.